Hello and welcome to this video tutorial on use of internal ADC of Peak microcontroller. So as you know, a Peak microcontroller has internal ADC which is of 10 bits and 8 analog channels are there. So we will try to write a program so that I will be making use of that internal ADC. So for that, you have to install MPLAB. So if MPLAB is installed, then you have to create a project. So go to the project wizard. In project wizard you have to select a particular microcontroller. So we will select PEAK 16F877A microcontroller. Then you have to select the active tool suite. So for as it is assembly language programming, we will use MPASM as the tool suite. Next it will ask you to create a project. So in a particular folder you create a project. So what you are doing is, I have one folder called as internal ADC in my documents. So there I create a project. Let us give the name to the project as internal ADC itself. So this is the project I am creating. Next it will ask you to add some already existing files. So I will skip this part. So now what you have to do is, you have to type what you can say ASM file or your program here in the editor, and after typing your program you have to save this particular program with the extension .asm. So as it is your assembly language code, so you have to save it with the extension .asm. So that gets saved in the same folder in which project is been created. So now after creating that, I have already that file created. So that ASM file you have to add to your project. So I have already this internal ADC program file available. So that file you have to add to as a source project. So now let us discuss what this particular program is first. So talking about this particular program, so just this program starts with this is list P, so which tells that which processor, so it is used to define the processor. Then there is a hash include P16F877A.inc file. So this file you include because later in your program you are going to use the names of the register instead of their addresses. So there is mapping done between the names and addresses in this particular INC file, so that in my program, let us say here I am using port D directly as the name, so automatically this port D will be replaced by its address. So for that you need to include. Then this is the configuration word. So this is to configure hardware module of the PEAK microcontroller. Then org00h, so this is where I start my code, and then immediately I write go to main, because I know that at address 0004 this address is the interrupt vector location. As I am not using any interrupt for this particular program, I will write just instruction retfi. So if an interrupt occurs, then just I will return to the main program. Now so this is where your main program starts. So the main program starts with the assembler directive bank cell. So this bank cell assembler directive is used to select a particular bank. Now port D is present in bank 0, so we need to select bank 0. We need to select bank 0 so that we can access port D. So I have selected the bank 0. Instead of selecting bank through the status register, we can use bank select what you can say as a assembler directive. Now next is clear file port D. Now I can deal with the port D register. So to understand that, so see what is happening is, if you see the organization of the memory for the PEAK microcontroller, you will come to know that this is the memory organization where the TRISD registers are present in bank 1, port registers are present in bank 0, and talking more specifically about our ADC module, so there is ADCON 1 register which is present in bank 1 and ADCON 0 is present in bank 0. So accordingly bank selection should be done. So now this is to select the bank 0, then I deal with the port D register, and then what I do is I clear it. So the output on that port D will be 0. Prior to that, I load this particular value in the working register, and then I move it to the ADCON 0. So if you see ADCON 0 register format, you can observe that. So this is the format. So if I have this particular bit format, means this particular bit is 1 and this particular bit is 1, least significant bit is 1, means I am turning on that particular ADC module, and then what I am trying to get by making this particular bit 0 1 is, what I'm trying to do is I'm trying to have a clock frequency which is oscillator frequency divided by 8, because I will take care that this ADCON 0 bit is also 1. So combinedly these 3 bits will give me the clock frequency which is oscillator frequency divided by 8, that will be used by the ADC. Now this format I load in ADCON 0. Now I want to deal with the TRISD register. So TRISD register is present in bank 1. So I write bank select TRISD so that bank 1 gets selected. Then I clear this TRISD. So why to clear this is, what you will be doing is ADC output you will connect to a port D through LEDs. Means to port D we will connect different LEDs. So when I clear TRISD, port D will be configured as output port, so that I can output some data onto those LEDs, and those LEDs will glow according to the data output. So what I do is ADC output I output onto the port D. So according to the ADC output, the port D contents will vary. Now next is this format I load in ADCON 1. So again, if you check the ADCON 1 format, so if I make it 1110, so what I am trying to do is 1110, this format makes what you can say only one analog input pin, then VDD VSS will be the reference voltages, means plus V reference and minus V reference will be VDD VSS itself, and only AN0 will be the analog input. So this is what configuration you are making for ADC. So I load it into the ADCON register. Now next again I select port D, bank select port D. Why? Because the ADCON 1 is present in bank 1. Now I want to deal with port D which is in bank 0. So I again select this bank select port D. Then what I do is bit set file ADCON 0 comma go. So what happens because of this is, if I select if I set ADCON 0 bit number 0, it is just to enable this particular ADC module itself. So if I make this ADCON 0 bit set, then what it does is it turns on the ADC module. So ADC module is powered up. Okay, so next what I do is again, once the module is powered on, based on what analog input you have, ADC will start doing the conversion, and when conversion is over, it will make that go oblique dunbar pin 0. So what I do is I poll for that particular bit bit go oblique dunbar of ADCON 0. Means here the conversion is started, so you wait till the conversion is over. How you will come to know that conversion is over? What ADC does is it makes that go oblique dunbar bit as 0 after conversion is over. So if that bit is clear, then only I skip the next instruction. Till it is not clear, I just wait. I wait for the conversion. Now next what I do is, whenever conversion is done, the conversion is available in the result register. Again, if you see the ADCON 1 format, this particular bit is ADFM bit, and I made it 0 so that the alignment of result is left alignment. Okay, so most significant bits of the result, means 8 bits, are available in an ADRESH register. So then when the conversion is over, what I am doing is the contents of that result register I am moving to the working register, and working register contents are moved to the port D register. Okay, and again what can be done is, if you are using interrupt for this ADC, then you need to clear that interrupt flag, because that flag is automatically set whenever conversion is over. Okay, and then this program I keep in loop. So this is the program for using internal ADC for the PIC microcontroller. If you build the target for this particular program, then what you expect the message is build succeeded without any error. When I get this particular message, then what I can do is I can check whether really I am going to get the output or not. So for that, what can be done is go to the debugger, and then as this involves some hardware, you can use Proteus VSM as the debugger. Sometimes this option may not be visible in your installation. In that case, separate Proteus installation you are having, so that that particular exe file you can open. So this window you will get. Then you have to open the design for this particular simulation for debugging. So already I have this particular design file which is available. So according to our program, this is the design file, because already we know that AN0 is the analog input, only analog input available. So to that I have connected this analog input. So I have connected it through port, and then this voltage is measured, and then I am outputting the data, which is this analog input will be taken by the ADC module. It will convert into digital, and that digital result I am making it its output onto what we can say port D. So what I have done is, to the port D LEDs are connected. So now I want to check whether my code is working or not. So what I need to do is, I need to add hex file for this particular project. So this hex file gets created in the folder in which you have created the project by by the name of the project. So already internal ADC program hex file is there, so I attach this particular hex file for the simulation. And then what you have to do is, you can run this simulation. Step by step simulation is also possible, but as this program does not involve any register values and changes in the registers, okay, so what we will do is, we will run this program directly. So this is how you can run this program. So when I run the program, now see, presently what I am observing is, all means if I make this particular input as 0, analog input is 0, its digital conversion will be 0, and that is what I output onto port D. So all LEDs are off, and then what I do is, I increase this particular resistance value. Accordingly the voltage will increase, and accordingly its conversion will increase. So if I apply maximum voltage, which is around 5 volt, so then what happens is, almost all LEDs are on. So this simulation shows how I can use internal ADC of the PEEK microcontroller. Thank you.